Hello and welcome you all in the problem solving class of the course Principles of Signals and System. I am Vivek Kumar Srivastava, a PMRF Research Scholar of Antenna and Microwave Research Laboratory, Indian Institute of Technology, Roper, and TO of this class. So, in the previous class, we have covered the various topics such as Laplace transform, where we have seen that why we are using this Laplace transform, how to evaluate the Laplace transform of any system or signals, and then we have seen the various properties uh, by which we can evaluate the Laplace transform easily, and at last we have seen the inverse Laplace transform. So the topic of today's class are the jet transform, where we will see basics of jet transform, followed by properties of jet transform, and in the last we will see inverse of jet transform. So let us start. So jet transform is basically a discrete time counterpart of the Laplace transform. So in the previous class we have seen that for analyzing complex signals, which is basically a continuous time signal, we are generally employing Laplace transform, where uh, we will convert the time domain signal into corresponding frequency domain signal, and then we will analyze the signal, because sometimes for the complex signal to analyze that signal in frequency domain are very easy. Okay, so that's why we are using Laplace transform. Okay, but the limitation of Laplace transform is that this Laplace transform we can only employ for continuous time signal. We cannot use the Laplace transform for evaluating the for analyzing the discrete time signals. Okay, so for this analyzing such a discrete time signal, we will use jet transform. Okay, so as I said, this jet transform is basically used to evaluate uh, or say analyze the discrete time signals. Okay, so basically this jet transform in the jet transform, what we are doing, we are basically uh, solving the discrete time sequence and analyzing the system uh, in the complex frequency domain, which is also known as jet domain. Okay, so basically what we are doing here, we are basically converting the time domain signal into corresponding jet domain signal or say sequence, and then we will analyze this signal. Okay, so basically by doing this we can reduce the time and effort required to analyze any discrete time sequence. Okay, so that's why we are basically using the jet transform. So I hope this motivation that why we are using this jet transform is clear to you. So now one can ask that where we will use means what are the various application where we can employ this jet transform. So basically there are few application where we can use this jet transform, like they are digital filter design, where we are using basically jet transform, and for analyzing the sample data control we are using the jet transform method. Okay, so there are some basic application where we are mostly using jet transform. So now let us move ahead and see that how to evaluate the jet transform. Okay, so like if suppose any arbitrary discrete time sequence, or say x of n, is given to you, so for evaluating the jet transform of this sequence, what we will do we will use this mathematical expression for evaluating the corresponding jet transform. Means for converting the discrete time sequence into corresponding uh, jet domain, we will use this expression. Okay, so what is basically this expression? So here x of jet basically denote the corresponding jet domain. Okay, signal in corresponding jet domain, and for evaluating we will use this expression, that is n varying from minus infinite to infinite x over n into z raised to the power minus n. So we are basically using this expression. By using this we can easily evaluate the jet transform of any discrete time sequence. Okay, here basically z is a complex variable. Okay, it is basically a complex variable. So this uh, expression is also known as double sided or bilateral jet transform. Okay, so like here we you can see that n is varying from minus infinite to infinite. So here this is also known as double sided or bilateral jet transform. And one more thing that I forget to uh, tell you, that here n is basically an integer value. Okay, here n is basically an integer value, means n can be 0 plus minus 1 plus minus 2. So basically, as we know that this discrete time sequence is basically defined only for integer values, so that's why here n we will take as a integer value. Okay, so as I said, this is basically the double sided or the bilateral jet transform. Okay, so by using this expression, we can easily evaluate the jet transform of any signal. Okay, so one more important thing is that for existing any for existence of any jet transform, this expression should be converged, and this expression will only be converged when this summation term basically converged, then only this x of z exist. Okay, and if suppose this summation expression will not converge, so in that case we cannot define the z transform of any that signal basically. Okay, so it is important that for evaluating a jet transform of any signal, this summation term should converge, then only we can evaluate the jet transform of any signal. Okay, so this is basically the most important property. Okay, so the range of value of z for which the above equation converge are basically known as the region of convergence. So this is known as the region of convergence. Okay, so basically if suppose this is my z domain. Okay, so here if this is basically the real part of z and this is basically the imaginary part of z, so uh, here basically we are varying the z. Okay, so the range of value of z for which this expression will converge is known as the region of convergence. So this region of convergence we can see in broad detail way in the upcoming slide. So here like the various properties of region of convergence that we will see and try to understand that what is basically this region of convergence is. So basically the first property of region of convergence is that the region of convergence should not contain any poles. Okay, so like if suppose we are evaluating the jet transform of any sequence x of n. Okay, so this x of n is x of z, once you evaluate it, comes as a rational function, means it has both the numerator as well as denominator term. Okay, so uh, poles are basically defined where denominator term will be equals to 0. So by using this we can evaluate the poles of any uh, discrete time sequence. Okay, so basically once you evaluate the pole and you see that whether it is within the region of convergence of the jet transform or not, so you will find out that uh, the poles will not contains within the region of convergence. So basically this is the first property of the region of convergence. The second property of the region of convergence states that the ROC for a finite duration causal sequence is the entire z plane except for z is equals to 0. So first of all we have to understand that what is basically this finite duration causal sequence. Okay, so basically if suppose this is my signal in discrete domain. Okay, so like this signal is basically defined only for positive value of n and for definite values of n, let us say. Okay, so like here 1 2 3 dot 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 n. Okay, so here you can see that it is defined only for, yeah. So here, uh, like we can see that this sequence is basically defined only for positive values of n, and this n is basically a limit, this is basically a finite value. Okay, n is basically a finite value. So this is basically known as finite duration causal sequence. So for this kind of sequence, once you evaluate the jet transform, okay, so you will obtain jet transform like x of 0 plus x of 1 z raised to the power 1 minus 1 plus dot 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 x of n minus 1 z raised to the power minus n plus 1. Okay, so from where we evaluate this, so by using this expression basically we are evaluating the jet transform of this uh, finite duration causal sequence. So once you evaluate the jet transform of this finite duration causal sequence, so you will see that this uh, jet transform of this signal contains the term that is 1 over z, means it has a pole at z is equals to 0. Okay, and we know that from property 1 that ROC should not contain any pole, so that's why here ROC will be entire z plane except z is equals to 0, because at z is equals to 0 one pole will be exist. Okay, so that's why this property states that for finite duration causal sequence the ROC will be entire z plane except z is equals to 0. So like here we can see that ROC is plotted, uh, just a moment. Yeah, so like here we can see that ROC is plotted. So entire z plane is basically the ROC except z is equals to 0. Here like z is equals to 0, so this z is equals to 0 will not be there in the ROC. Okay, so this is the second property. So now moving ahead, the third property of region of convergence. So the third property of region of convergence state that for a non-causal finite duration sequence, the ROC is basically the entire z plane except z is equals to infinite. Okay, so first of all we have to see that what is this basically the uh, non-causal finite duration sequence. So like in the previous uh, uh, property we have seen that finite duration causal sequence is basically the sequence that exists for positive value of for positive values of n and the finite values of n. Okay, whereas this is just this non-causal finite duration sequence is just the inverse of basically uh, this finite duration causal sequence. Okay, so here this is sequence is basically defined only for finite value of n and where n will be negative values. Okay, so like here we can see that this sequence x of n is defined only for negative values of n, and this n will be a finite value. Okay, so this is basically a non-causal finite duration sequence. So for such a sequence in time domain we can define it like x of n is equals to summation n is equals to minus n to minus 1 x over n. Okay, so for such kind of sequence once you evaluate the jet transform you will get the jet transform as x over x of minus n z raised to the power n plus dot 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 plus x of minus 1 z. Okay, so here if you can see that here this expression will only converge for all values of z except z is equals to infinite, means z is equals to infinite should not be there in the ROC. Okay, so like here I've plotted the uh, region of convergence for non-causal finite duration sequence. So here you can see that ROC is exist for all values of z except z is equals to infinite, which will exist here. Okay, so this will not basically present in the ROC. ROC is this one. Okay, so I hope this property is clear to you. So now moving ahead, the fourth property states that the ROC for a finite duration two-sided sequence is the entire z plane except z is equals to 0 and z is equals to infinite. So this property is basically the combination of the last two property. Okay, so like here the finite duration causal sequence is exist for all positive values of n where n will be finite value, whereas non-causal finite duration sequence is basically exist for negative values of n where n will be basically a finite value. So this property is basically a combination of these two signals. Okay, so here let us say this is my signal. Okay, so here n will be both positive as well as negative. Okay, as well as this n will be finite here. Okay, so such kind of signal is represented as, sorry, x of n is equals to summation n is equals to minus n to n. Let us say it is minus n and this is n. Okay, x of n. Okay, so this finite duration two-sided sequence is represented by this expression, and for this expression once you evaluate the z transform you will get the z transform as x of minus n1 z raised to the power n1 plus dot 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 x of minus 1 z plus x of 0 plus x of 1 z raised to the power minus 1 plus dot dot x of n2 z raised to the power n2. Okay, so like here if you can see that it contains both the term z as well as 1 over z. Okay, so for z term the ROC should not contains z is equals to infinite, whereas for this 1 over z ROC should not contains z is equals to 0. Okay, so that's why the ROC of such kind of finite duration two-sided sequence is the entire z plane except z is equals to 0 and z is equals to infinite. So now moving ahead, the ROC for a infinite duration right-sided sequence is the ex is the exterior of a circle which may or may not include z is equals to infinite. Okay, so like first of all we have to see that what is infinite duration right sided sequence. Okay, so this is, let us say this is x of n, this is n. Okay, so finite duration right sided sequence means sorry, infinite duration right sided sequence means it will exist only for positive values of n. Only for positive values of n this signal will exist, and here n will be infinite basically. Okay, so n will be infinite. So such kind of sequence are known as infinite duration right sided sequence. Okay, so for such kind of sequence once you evaluate the z transform you will get 1 over z term. Okay, so yeah, 1 over z minus a term. Okay, so for this kind of signal, sorry, for this kind of jet transform you will see that the ROC of this uh, kind of sequence will be exterior to this radius r1. Okay, this circle r1 exterior to this circle the region of convergence will exist. Okay, the region of convergence will not exist inside this circle for right sided sequence. Okay, whereas in contrast to the right sided sequence in the left sided sequence, if you plot the ROC, so you will get that it will be interior to the circle. Okay, so like here I have plotted the ROC for left sided sequence, so here we can see that ROC is interior to this circle. Okay, whereas for right sided sequence this is basically exterior to this circle. Okay, so I hope these properties will be clear to you. So now moving ahead, this is the last property which states that ROC of an infinite duration two-sided sequence is a ring in the Z plane. Okay, so if suppose you have two-sided sequence, okay, means x of n is basically defined as summation n is equals to minus infinite to infinite, uh, yeah, x of n. Okay, so this is basically the sequence. Okay, let us say this is some another signal that is x1. Okay, so this sequence is defined in this term. Okay, so means it contains both the positive values of n and negative values of n, as well as this n will be infinite. Okay, so this is known as infinite duration two-sided sequence. Okay, so for this kind of signal, once you plot the ROC, so you will get that ROC is basically a ring shape. Okay, so like here I have plotted the ROC is in the form of ring shape. So this property we can easily understand by using an example. Okay, so here we will I will demonstrate you that how to evaluate the jet transform of a signal, as well as how to plot the ROC. So here let us say a signal is given to us, that is x of n is equals to, for positive value of n, this x of n is defined as minus 1 by 5 raised to the power n, whereas for negative values of n, this x of n is defined as minus 1 over 3 raised to the power n. Okay, so we have to here evaluate the jet transform and plot the ROC of this signal. Okay, so let us see that how to evaluate the jet transform uh, as well as ROC of the signal. So as we know that jet transform of any sequence is defined as n is equals to minus infinite to infinite x of n z raised to the power minus n. Okay, so basically we have to put this signal here. So like here if we can see that uh, for for positive values of n, the value of this signal x of n is minus 1 by 5 raised to the power n. So this is basically summation n is equals to minus infinite to infinite, sorry, yeah, just a moment. Summation n is equals to 0 to infinite minus 1 by 5 raised to the power n z raised to the power minus n, plus summation n is equals to minus infinite to minus 1. Okay, this will be minus 1 by 3 raised to the power n into z raised to the power minus n. Okay, so if you evaluate this integral, so this will be n is equals to 0 to infinite, this will be minus 1 by 5 z raised to the power minus n minus 1 raised to the power n, plus here I am just interchanging the uh, this n to my n to minus m. Okay, so here the value of m will be 1 to infinite minus 1 by 3, yeah, here, or you can directly write it like 3 z raised to the power m. Okay, so once you evaluate uh, this expression, so you will get, this is basically a GP series, okay, which is starting from 1 plus minus 1 by 5 raised to the power minus 1 plus minus 1 by 5 raised to the power minus 1 square plus dot 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 plus this term, okay, which is basically minus, because here one minus is there, okay, which I am taking common, means outside this summation, and this will be 3z plus 3z square plus 3z cube, okay, and so on. Okay, so as we know that summation of uh, summation of a GP series, okay, having r as a common factor, is defined as 1 over 1 minus r. So here r is basically minus 1 by 5 raised to the power minus 1, minus, for this term this will be a in bracket, sorry, divided by 1 minus 3z. Okay, so by using this expression we can evaluate the z transform. So like here, if you simplify this expression, you will get this uh, xz, okay, which is basically representing the z transform of this signal. Okay, so that's how you can evaluate the z transform. Whereas for evaluating the, yeah, just a moment, let me remove this. Yeah, so basically for evaluating the ROC, we can see here that this x of z is basically taking, uh, considering two terms, okay, that is, first one is this one, whereas the second one is this one. So from here we can see that the first summation is basically corresponds to the right sided sequence, whereas the second expression is basically correspond to the left sided. Okay, so as we know that for right sided sequence, the ROC is basically defined as mod of z is basically greater than mod of 1 by 5, whereas for left sided sequence this mod of z is basically less than mod of 1 by 3. Okay, so once you plot this, so like here, let us suppose that this is unity circle. Okay, this is unit circle, r is equals to 1. So this 1 by 5 means this will be somewhat here. Okay, let me change the color. So this will be here, that is z is equals to 1 by 5, whereas the second one, that is z is equals to 1 by 3, is this circle, that is green circle. So ROC of the first, that is right sided sequence, is basically z is greater than 1 by 5. Okay, so like here z will be greater than 1 by 5. So this portion is basically the ROC of the first right sided sequence. Okay, whereas for left sided sequence this z will be less than 1 by 3, means this one. Okay, so the ROC of the final sequence is basically the intersection of these two. Okay, so ROC of the final sequence is basically the intersection of these two, means this one. Okay, let me, so ROC will be this one, means this will be a ring shape. Okay, so ROC is basically a ring shape structure for this kind of sequence. Okay, so I hope this problem is clear to you. So now moving ahead, see, here is the various properties of the jet transform. So the first property is the linearity property. okay, linearity property. So if suppose x1n and x2n are the two sequence with the z transform is defined as x1 of z and x2 of z, and the ROC is basically r1 and r2 respectively, then the z transform of the linear combination of x1n and x2n is given as z of x1n a1 x1n plus a2 x2n. So z transform of this sequence is basically defined as a1 x1z plus a2 x2z. Okay, and ROC of this linear combination of x1n and x2n is basically defined as ROC is equals to r1 intersection r2. Okay, so by using this property, if suppose any signal is given to us which is basically a combination of different signals, okay, so we can easily evaluate the ROC Z transform of this linear combination of signal by individually evaluating the Z transform of uh, the linear combination of signals. Okay, and then by using this property we can evaluate the Z transform of overall signal, okay, as well as the ROC. Okay, so ROC is basically the intersection of all the uh, individual sequence that is basically forming the linear combination of any signal. Okay, so this is the first property, that is the linearity property. Now the second property is the time reversal. Okay, so if suppose x of n is sequence with a z transform of x of z and ROC is r, then the z transform of the time reversed sequence is defined as z transform of x of minus n is defined as x of 1 by z. Okay, and ROC is also inverse, basically 1 over r. Okay, so this is the second property, that is time reversal property. The third property is basically the scaling in the z domain. So if suppose a sequence x of n is given to you having the z transform x of z, and ROC is defined as r. Okay, so for evaluating the scaled z transform of scaled signal, that is x of an, or say x of a raised to the power n into x of n. Let me change this. Yeah, we have to evaluate the z transform of a raised to the power n into x of n. Okay, so z transform of this signal is basically defined as x of a inverse into z. Okay, and ROC will also be changed here. ROC will be defined as a mod of a into r. Okay, so like if x of n is known to you and the corresponding, sorry, if corresponding to the x of n you already know that what is the x of z, means in z transform is known to you. So for evaluating the scaled function, that is a raised to the power n x of n. Okay, so for evaluating the z transform of this signal, what we will do, we will just change the parameter z as a inverse into z, and the corresponding ROC will also be changed. Okay, so now moving ahead, the fourth property is the time shifting property. Okay, so time shifting property states that if corresponding to this signal, that is x of n, z transform is known to you, that is x of z, and ROC is defined as r. Okay, so for evaluating the z transform of delayed sequence, okay, z transform of delayed sequence, that is x of n minus k, the corresponding z transform is defined as z raised to the power minus k into x of z. Okay, and the ROC will remains the same. Okay, ROC will not change in case of time shifting. Okay, so this is basically the fourth property. So basically shifting in time domain will result in multiplication in delayed uh, multiplication of delayed function in corresponding z domain. Okay, this is basically a time shifting property and ROC will not change here. So now the fifth property is the differentiation in z domain. Okay, so like if this uh, x of n corresponding to this x of n, x of z is known to you, ROC is also known to you. So now if suppose we have to evaluate the uh, z transform of this modified signal, that is n x of n. Okay, so the corresponding uh, z transform is defined as minus z into d by dz of x of z, and ROC here will be same as the x of z. Okay, so this is basically a differentiation property. Now the sixth property is convolution of the two sequence. Okay, so if x1 n and x2n is known to you, and the corresponding x1z and x2z you have evaluated with the ROC is defined as R1 and R2. Okay, so if suppose you have to evaluate the z transform of this convolved signal, that is x1n convolved with the x2n, so the corresponding z transform is defined as x1z into x2z. Okay, and ROC is basically intersection of individual ROC. Okay, so this is basically the convolution property of the two signal in z domain. Now here are some different properties that you can see. Okay, but here we are not using this property. This is just for uh, I'm adding here so as to give you an insight, but you can cover it by yourself due to time constraint. I am directly uh, moving ahead for towards the uh, problem. Okay, so now we will see that how to utilize all those properties that we have covered till now, and how to solve the problems. Okay, so like here we have to find out the z transform of this signal, that is minus u and minus u of minus and minus 1. Okay, so now what we will do here, we will use the property for evaluating the z transform of this signal. Okay, so first of all, for evaluating the z transform of this signal, we have to know the z transform of u of n. Okay, so basically here u of n is the base signal. By using the different property of the z transform, we can easily convert this signal into this signal. Okay, and try to evaluate the corresponding z transform. So first of all, we will see that how to evaluate the z transform of this signal, that is x of n, that is u of n basically. Okay, so as we know that z transform of this signal is basically defined as from 0 to or let us say minus infinite to infinite u of n into z raised to the power minus n. So now as we know that u of n is basically defined from 0 1 2 up to infinite. Okay, so that's why here summation range will change from 0 to basically infinite z raised to the power minus n. So now once you evaluate this summation, you will get summation as 1 is z raised to the power minus 1. Okay, and here as this is a infinite duration right sided sequence, so basically mod of ROC is basically mod of z will be greater than mod of 1. Okay, or you can say mod of z will be greater than 1 here. Okay, so this is basically the z transform of unit step sequence with the corresponding ROC. Okay, so now once we know the z transform of this sequence, so now once we know the corresponding z transform of this sequence, that is u of n, Now we will use the property so as to evaluate the jet transform of this sequence. Okay, that is given in the problem. Okay, so now first of all we will use the time shifting property. Okay, so jet transform of u of n minus 1. So as we know that this is a delayed signal, means delayed in time correspond to the multiplication of delayed jet in the jet domain. Okay, so here z of u of n minus 1 is basically defined as z raised to the power minus 1 into x of z. Okay, which is basically z raised to the power minus 1 1 over 1 minus z inverse, which is basically z inverse into z over z minus 1, which is basically 1 over z minus 1. Okay, and here ROC will not be changed. Here ROC will be mod of z will be greater than 1. Okay, so now we have used the time shifting property. Now we will move ahead and use the time reversal property. Okay, so what we will do here, we will just change n with minus n. Okay, so this is known as time reversal property. So once you apply the time reversal property, you will get u of minus n minus 1. So the corresponding jet domain, the corresponding jet transform is defined as 1 over z minus 1. Okay, and ROC will also be changed, that is 1 over z will be greater than 1. So here ROC means mod of z will be less than 1. So this is basically the ROC, and once you evaluate this expression you will get z over 1 minus z. Now we have used the time reversal property so as to evaluate u of minus n minus 1. So now we have to just use the negative sign so as to uh, evaluate this signal that is given in the problem. Okay, so we will use this z of minus u of minus n minus 1. So once you evaluate the jet transform of this, so this will be minus will be multiplying in both side. Okay, so this will be minus z over 1 minus z, or you can also write this as z over z minus 1, and ROC will be same here. Okay, so that's how you can apply all these properties that we have covered till now so as to evaluate the jet transform of any complex signal. By using this property we can easily evaluate the jet transform of any complex signal if we know basically the jet transform of any simple function. If we know, then by using this property we can evaluate the jet transform of any complex signals. Okay, by using this property we can easily evaluate. So now moving ahead, the next problem is we have to find the jet transform of sequence x of n, which is defined as b raised to the power n u of n. Okay, so uh, we will use this expression, that is x of z summation n is equals to 0 to infinite because u of n is here. Okay, and this will be b of n z raised to the power minus n. So once you evaluate you will get 1 over 1 minus b z inverse. Okay, and this will be, yeah, z over z minus b. And as this sequence is basically a right sided sequence, so mod of z will be greater than mod of b. Okay, so that's how you can evaluate the jet transform. Or by using the property as well you can evaluate, like here we are basically using the scaling property because a function uh, because a multiplier b of n is multiplied with u of n. So for u of n, like we know the jet transform is defined as 1 over 1 minus z inverse. Okay, so if the signal is b of n u of n, so in that case the jet transform will be, A into Z inverse. Okay, so sorry, B into Z inverse. So once you put this in the expression, you will get B Z inverse. Okay, will be equal, which will be equals to Z over Z minus B, and the region of convergence will remain the same. Okay, so that's how you can evaluate by using the expression as well as by using the property of the Z transform. Now moving ahead, here we have to evaluate the Z transform of x of n, which is defined as n into u of n. So here we will use the multiplication property, or sorry, differentiation property in Z domain, so as to evaluate the Z transform of this signal, that is n into u of n. So like, differentiation property states that the Z transform of n into x of n is defined as minus z d by dz of x of z. Okay, so x corresponding to x of n, that is basically u of n. Okay, this will be equal sign. So corresponding to that, we know that the x of z is defined as z over z minus 1, where ROC will be mod of z will be greater than 1. Okay, so by using this we can easily evaluate the z transform, which will be defined as minus z d by dz of z over z minus 1. Okay, so now we can differentiate this, and we will get like denominator into d by dx of numerator minus numerator into d by dx of denominator over 1 minus z square. Okay, so now you can evaluate this, and you will get the final expression as z over z minus 1 square. Okay, and ROC will be mod of z will be greater than 1. Okay, so that's how we can use the differentiation property so as to evaluate the modified signal, z transform of modified signal, that is n into x of n. So now the second problem is basically the extension of this previous problem. Okay, here we have to again multiply this signal, that is n into u of n, which is the previous problem, with one more n. Okay, so the overall signal will become n square into u of n. Okay, so here the fine corresponding to this, the z transform is defined as minus z d by minus z square into d square by dz square into x of z. Okay, here x of z is equals to 1. Yeah, this will be equals to 1 minus z inverse, or say z over z minus 1. Okay, so by using this differentiation property, you can easily evaluate the z transform of this signal. So I am leaving this exercise for you. You can uh, you can easily evaluate the z transform of this expression by using this differentiation property. Okay, so now moving ahead, uh, here we have to find out the z transform of x of n, which is basically a uh, sine function, that is sine of omega n into u of n. So this sine of omega n is basically into u of n is basically defined in terms of exponential function as 1 over 2j e raised to the power j omega n minus minus e raised to the power minus j omega n into u of n. Okay, so now once you evaluate this u of n is multiplied inside this bracket, so this will be equals to e raised to the power j omega n minus e raised to the power minus j omega n. This will be u of n, this is also u of n. Okay, so this is basically a signal, and here we will use the linearity property. So this is my first function and this is my second function. Okay, so I will evaluate the jet transform of these two signals individually, and then I will uh, basically, using the linearity property, I will evaluate the overall jet transform of this sine of omega n into u of n. Okay, so that's how we can evaluate the jet transform of sine of omega n into u of n. So now we will evaluate the jet transform of this signal, which is basically defined as jet transform of this signal. Okay, so now we will, this 1 over 2j is basically common here, so I have taken this term as common. Now I will evaluate the jet transform of these two signals individually. So this is basically defined as z over z minus e raised to the power j omega minus z over z minus e raised to the power minus j omega. Okay, so if you further solve this, you will get this expression, and here ROC is defined as mod of z will be greater than 1. Okay, so once you solve this expression, you will get this final expression. Okay, and as well as ROC. Okay, similarly, by using the previous method, you can find out the jet transform of cos of omega n into un. So first we will express this cos of omega n into un in terms of exponential, complex exponential term, which is e raised to the power j omega n plus e raised to the power minus j omega n by 2. Okay, so by using this we can evaluate the uh, complex exponent. We can represent basically the uh, cos of omega n in terms of complex exponential. And now we will use the linearity property, and we will individually evaluate the jet transform of these two terms so as to evaluate the final jet transform. And once you evaluate the jet transform, you will get this expression. Okay, so now moving ahead, yeah, here we have to find out the jet transform of sequence x of n is equals to u of n minus u of n minus 5. Okay, so if you plot this this signal, you will get u of n is basically defined for n is equals to 0, n is equals to 1, 2, 3, 4, 5, 6, 7, and all. Okay, this will be 0, 1, 2, 3, 4, 5, 6, 7, and so on. And once you plot the another signal, that is u of n minus 5. Okay, so you will get this signal that it will start from n is equals to 5, 6, 7, and all. Okay, so now you have to subtract these two signals so as to get this u of n minus u of n minus 5. Okay, so once you evaluate this, so the final signal becomes this, start from n is equals to 0, 1, 2, 3, and 4. 0, 1, 2, 3, and 4. Okay, so this is basically x of n. Okay, so for this sequence we have to evaluate the jet transform. So once you represent this signal x of n as summation n is equals to 1, or say, yeah, 1 to, sorry, this will be 0 to 4 delta of n minus, let us say this is m. Okay, m. Okay, so that's how we can represent the x of n signal. Okay, so now once you evaluate the x of z, you will get summation n is equals to 0 to 4. Okay, and this will be, or say this is infinite delta of n minus m, sorry, this will be n. So now once you evaluate this expression, you will get also 1x m will be 0 to 4. Okay, so once you evaluate this expression, you will get 1 plus z raised to the power minus 1, z raised to the power minus 2, z raised to the power minus 3, and z raised to the power minus 4. So once you evaluate this summation of this series, so you will get 1 into 1 minus z raised to the power minus 5 over 1 minus z raised to the power minus 1. Okay, so this you can further evaluate as z minus 1. Okay, so this is basically the z transform of this signal. Okay, and as we can see here, so now we can further evaluate this as z as, yeah, this will be z raised to the power 5 minus 1 over z raised to the power 5 into z minus 1. So this z will cancel. So from here we can see that, yeah, so from here we can see that denominator contains two poles, that is 0 and 1. So ROC will be entire z plane except z is equal to 0 and 1 here. Okay, so I hope this problem is clear to you. So now moving ahead, uh, the second for, yeah, so now the next so now the next topic is inverse jet transform. Okay, so here basically, actually this will be inverse jet transform only. So now the next topic is inverse jet transform. So basically, if suppose this x of z is known to you, so one may ask whether we can find out the value of this signal or not. So the answer is yes. By using the inverse jet transform, we can easily evaluate that which kind of signal we can use so as to get this x of z. Okay, so this is basically an inverse problem where x of z is known to you, and by using this x of z, we are evaluating the value of x of n. So by using this uh, integral, we can easily evaluate the inverse jet transform. Okay, but the problem with this integral is that for the complex uh, uh, for the complex value of x of z, to evaluate this integral is very difficult. So for that so for evaluating the inverse jet transform of that complex x of z, we are basically using the partial fraction expansion method for evaluating the inverse jet transform. So what we will do here, we basically using the inverse jet transform by using partial fraction expansion. Okay, so here we represent the jet transform as a rational function. Okay, means in terms of numerator as well as denominator of this uh, complex parameter of z. Okay, so here is the rational function of z, which is basically representing the x of z here. Okay, so now what we will do, we will first try to evaluate the poles. Okay, corresponding to all pole, we will first simplify or say expand this in terms of partial fraction. Okay, so once you evaluate this, you will get this expression here. Basically, pi are the poles and ci are the coefficients. Okay, so this pole you can easily get by using this d of z is equals to 0. So by evaluating this, okay, you can easily evaluate the poles. Whereas for evaluating the coefficient, so as to simplify this expression, that is x of z, we will use this expression, okay, that is ci is equals to z minus 1, sorry, z minus pi x of z over z, okay. Whereas for repeated poles we will use this expression, okay. So no need to worry, I will basically take an example so as to make it clear for you. Okay, so now once you evaluate this uh, coefficient Ci and poles Pi, so we can write this x of z as z if you multiply this z, or say if you multiply z from both sides, so you will get it like this, okay. So this z and z will be cancel out, and you will get this expression. And by using the uh, inverse z transform of these signals, basically z over z minus p, which is known to us, we can easily evaluate the inverse z transform of any rational function, okay. So now let us take one example. So here let us say x of n is right handed sequence which is given to us. So now we have to determine the inverse jet transform for the function, okay. So here function is given to us. So by using partial fraction method we have to evaluate the inverse jet transform, and it is given in the question that x of n is basically a right handed sequence, okay. So first of all we have to basically represent this uh, uh, we have to represent this basically rational function in terms of simplified function, okay. So what we will do, we will basically take x of z and divide it by z. So this will be equals to z cube plus 2 z square plus 1 over z square z plus, sorry, z minus 1 into z minus zero point 0.5, okay. So now we will express this as a over z plus b over z square plus c over z minus 1 plus d over z minus zero point 0.5, okay. So here we have to just evaluate this coefficient a b c and d, okay. So like by using this formula we can evaluate the coefficient. So like here I am evaluating the coefficient a for you. So this will be equals to minus 2 minus 1 into d by, basically here the poles are repeated, okay. So that's why I am using the coefficient corresponding to repeated poles, okay. So d by dz z square z cube plus 2z square plus 1 over z square z minus 1 into z minus zero point 0.5, okay. So this z square will cancel, and now once you differentiate this and evaluate this, so you will get a as 6. Similarly you can find for b. So for that this will be equals to 2 minus 2 d by dz 2 minus 2, okay. So this differentiation term will cancel because 2 minus 2 will be 0 basically. So here differentiation will not be there, only you have to multiply z square 2z square plus 1 over z square z minus 1 z minus zero point 0.5, okay. So this will be cancelled, and you have to just replace z as 0. So once you put this z as 0, so you will get the value of b as 2. Similarly you can evaluate the value of c, coefficient c. So for that what we have to do, we have to just multiply the with the corresponding pole, that is z is equals to z minus 1, with this expression, that is z cube plus 2z square plus 1 over z square, z minus 1, z minus zero point 0.5, and replace the z as 1. Okay, so this z and z cancel, and once you evaluate, you will get the value of c as 8. Similarly, you can evaluate the value of d, so this will come as minus 13. So once you put the value of this abcd in this expression and multiply z from both sides, so you will get this expression, final expression. So now by using the inverse Fourier, inverse jet transform of uh, this known function, we can easily evaluate the jet transform of overall function. Okay, so like for uh, for 6 we know that corresponding to x of delta of n, the jet transform will be equals to 1. So that's why when once you take the inverse jet transform, delta of n will come here. Similarly here, z inverse is there, means it is delayed in uh, or sorry, it is multiplication with z raised to the power minus 1 in the z domain. So corresponding to that, you will get signal delta of n minus 1. So that's why delta of n minus 1 is came here. Similarly, we have seen that corresponding to u of n, the corresponding z transform is defined as z minus 1. So that's why u of n is came here, and here also a raised to the power n into u of n. Here a is 0.5 basically. Okay, so that's how by using partial fraction method we can easily evaluate the inverse jet transform of any rational function. So I hope these problems will be clear to you. So with that, uh, this class is over. So I